Okay, so it's my pleasure to welcome Karthik Ganapathy from University of California, San Diego to talk today about GL-algebras and the Noetherianity problem.
Yeah, thanks, Scott, for introducing. And I also want to thank Tekin, who invited me to speak. I hope you can hear me clearly. Okay. And feel free to shout out questions. I can hear all of you reasonably well. So yeah, before I start, I want to give two kind of meta ideas that were integral to me proving this. The first is regarding characteristic 2, or generally low characteristics. So, when we are interested in studying representations of groups, there is essentially kind of three classes that it naturally divides into. So characteristic 0 is considered sort of the easiest in almost all cases. Then the second easiest is considered to be like very large characteristic. And then the third case would be small characteristic, where things get somewhat messy. This is true for finite groups, and happens in various ways for algebraic groups as well. But what in the kind of stuff that I do, which is broadly speaking, infinite dimensional algebra, and as well as many problems regard with us, when you're interested in stable properties, say work of Raiku and van der Burgert on sort of stable cohomology on flag varieties. Characteristic 0 is still the simplest, but low characteristic becomes the second easiest, and the larger characteristic becomes the hardest. So characteristic 2 somehow becomes the bridge between characteristic 0 and the other positive characteristics. And this will be clear in the talk, and hopefully by the end I'll be able to explain how I hope to generalize this to higher characteristics. But that's one kind of like meta idea to keep in mind. The second one is regarding exterior algebras. So in general, when you're interested in, say, combinatorial commutative algebra, where you might be interested in studying properties of monomial ideals and so on, the issue is that we always focus on polynomial rings, which I think is maybe a mistake, because when you are looking at polynomial rings, things become harder, and there are sometimes ad hoc statements about square-free monomial ideals and so on. Whereas if you're working in the exterior algebra instead, somehow every ideal is, every monomial ideal is somehow square-free. And this, because we don't investigate the exterior algebra, we kind of like jump to the polynomial ring immediately. We have sort of things are not as clear. Whereas I think the exterior algebra is something that we need to start like studying sort of more more kind of like comprehensively from a combinatorial commutative algebra perspective. So yeah, that's kind of two things, and hopefully both of this will be clear as to how it plays into this as the talk proceeds. So let me also say that the talk is divided into essentially kind of three natural parts. The first part is fairly elementary and combinatorial. It's some sort of like algebra combinatorics dictionary that I want to sort of that I will use to motivate the rest of the talk. The second part is where I'll introduce the main characters of the story. So those are GL-algebras. And the third part is will be my results. So, and most of this is fairly combinatorial, and yeah, feel free to ask me questions at any point in time. And especially the first part is fairly, follows from like first principles. So you should be able to follow it along. Okay. So let me just start with a basic setting. So I have a poset, and typically these posets are infinite. An ideal in this poset is an upwards closed subset. So that means that if you have a point of the poset in your subset, and anything bigger than that, those points are also there in your subset. And one way to create an ideal is you can just take a point in your poset and look at everything above it. That's, those like play the role of principal ideals. And more generally, we say an ideal is finitely generated if you have finitely many elements y1 through yn, such that the element the subset y is defined by all elements which are bigger than equal to yi for some I1 less than equal to I less than equal to n. Okay. And we say a poset X is Noetherian if all ideals of X are finitely generated. So, I mean, this is called term so because this is where you can essentially do like Noetherian induction in some sense. And there are a lot of other characterizations for when a poset is Noetherian. For example, it is also equivalent to demanding that you have no infinite anti-chains, which means no infinite elements which are pairwise incomparable, as well as not having the descending chain conditions. Those two conditions are equivalent to this condition. And a third condition, which is fairly useful, is the following. A poset X is Noetherian if and only if given an infinite sequence x1, x2, xn, and so on, there exists an infinite sequence of indices I1 less than I2 less than I3, such that xi1 is less than equal to xi2 is less than equal to xi3, and so on. So you can find an infinite subsequence which is ascending. And the idea basically is that if you look at the set of, if you look at the set of the ideal generated by x1, x2, and so on, they will be, if you think about your poset as some kind of like upwards tree, like the fact that it is Noetherian tells you that you will be in finitely many kind of branches. And since you have infinite indices, there will be at least one branch which has infinite indices, and you kind of like play this game of choosing, keeping on choosing like that. This is not that hard. So here are some examples of some Noetherian poset. So you have the natural numbers under the usual ordering is a Noetherian poset. So the ideals are just given by taking up natural number and looking at everything bigger than or equal to that. The integers, for example, is not Noetherian, and that's because if you look at the set of all integers, there is no minimal element, so it is not finitely generated. The whole poset itself is not finitely generated. Then another example is which is fairly useful is the set n to the r, where r is a fixed integer, a positive number, and the ordering is given by you say an r tuple is less than another r tuple if and only if like in each coordinate it's less than alpha I is less than equal to beta I for all I in R. And this is a Noetherian poset, and you can actually see this pretty easily by this lemma. Essentially, let's just do it for the n to the 2 case. If you have alpha 1, beta 1, alpha 2, beta 2, alpha 3, beta 3, which is an infinite sequence, then on the first tuple itself, you can choose an infinite subsequence which like is always increasing. So let's say it's alpha I1, alpha I2, alpha I3. And then you can look at the corresponding coordinate for beta I1, beta I2, beta I3. That will also have an infinite subsequence because the natural numbers itself is Noetherian. So therefore, you can, by combining both of these, you can get an infinite subsequence, which is strictly increasing. Are there any questions about what I just said? Okay, so it's not too difficult. And in some sense, if you look at like this picture that I took from Wikipedia, this line is, an ideal in n to the 2 is essentially if you look at this point, and you can see my cursor, right?
Yep.
Okay. If you look at this point, then the elements in the ideal are essentially like everything that's above this and to the right of this and on that side. And if you look at this xy equals 9 in n to the 2, it like cuts out this black curve, and it's finally generated by this the red dots given here. And in fact, this also shows that R to the 2 is not Noetherian as a poset. But so, and the reason I'm introducing these combinatorial gadgets is because I want to kind of see them as algebraic manifestations of like various theorems. So in particular, Dixon's lemma for me is the algebraic Dixon's lemma for me is the combinatorial manifestation of Hilbert's basis theorem, where Hilbert's basis theorem is the statement that the R variable polynomial ring is Noetherian. And the way you generally prove, I want to sort of give a broad stroke picture as to how these two are connected. So you first reduce the Noetherianity problem for general ideals in the R variable polynomial ring to monomial ideals by first defining an appropriate notion of leading term for every polynomial. Okay, that's something that you can do. And so this would essentially say that if you can show it for monomial ideals, that monomial ideals are Noetherian, then this implies that it's true, all ideals are Noetherian. Then the key observation here is that by associating, if you take an R, if you take a monomial x1 to the alpha 1, x2 to the alpha 2 to xr to the alpha r, you associated the point alpha 1, its exponent vector in n to the r. Okay, and so monomial ideals in the polynomial ring will correspond exactly to poset ideals in n to the r. And division in the R variable polynomial ring will correspond to the ordering that I've defined. So if you have two exponent vector alpha I and beta I, then each of the beta i's have to be bigger than or equal to alpha I for the corresponding monomials in the polynomial ring to divide each, the first one to divide the second one. And now Dixon's lemma implies the Hilbert spaces theorem, because now I have a poset that it defines. If you give me a monomial ideal, I look at the corresponding poset, it will be finally generated. So there'll be finitely many points in the lattice which generated. And the corresponding monomials in the R variable polynomial ring will generate the ideal that I studied. Okay, that's kind of in broad strokes how Dixon's lemma is the combinatorial manifestation of Hilbert spaces theorem. So now there's a fairly like more difficult result about Noetherianity, which I also say because this will give us like really interesting algebraic objects which are Noetherian. So if you give me a Noetherian poset X, I define the poset X star with a ordering that I'll define, where X star is a set of finite words with alphabet in X. And the ordering is given by, if you give me X1 to Xn, which is a word, and I say it's less than Y1 through Ym, if I can, so essentially like I can find a subword of Y1 through Ym, where pointwise of length n, where pointwise Yij is greater than or equal to Xj. So essentially, if you like look at, I mean, hopefully the mirror image doesn't mess things up, but if you have a 2-letter word and a 3-letter word, either I compare this way, or this way. And in that comparison, it has to be greater than or equal to. So for example, 1, 1 will be less than 2, 0, 2, because 1 is less than the first 2, and the second one is less than the third letter in the second word. Okay, and the key result of Higman, which goes back to the 50s, is that if you start with the Noetherian poset and consider the set of all words under this ordering, it's also Noetherian. And I'll quickly say how to prove this, because it's a nice trick that's fairly used in computer science and combinatorics in general, which is the sort of Nash-Williams theory of bad sequences. So if you give me so we will use the sort of, so let me say a bad sequence of words, W1, W2, W3 till Wn, where each of the Wi's are words, is I will call it bad if for all I less than j, we have Wi is not less than or equal to Wj under the ordering. So if X, and the point is that if X star is not Noetherian, the set of bad sequences is empty. Now I will build a minimal bad sequence. So among all bad sequences, I choose one where the length of the first word is the minimal. Then once I have chosen a bad sequence starting with W1 with length of W1 minimal, I look at all sequences that start with W1 and choose the one where length of W2 is minimal. And I keep on iteratively building a bad sequence like this. Okay. So at the end point, if you have chosen a sequence W1 till Wn, look at all bad sequences that start with W1 through Wn and choose one where the length of Wn plus 1 is minimal. And you can just keep on doing this. So once you've chosen a minimal bad sequence this way, the key trick now is you can look at the first letters of the Wi. So that will be, let's say it's X1, X2, X3, and so on, where Xi is the first letter of Wi. Now the key point is that because the poset that you started with was Noetherian, this will contain an infinite subsequence, which will be being ascending. And so somehow with this, you can like now cook up a bad sequence, which is more minimal than the one that I started with by kind of removing the first letter. And this is not too hard. I've kind of given you most of the ideas, and then you can essentially like get a contradiction this way. So this tells you that X star with this preceding ordering is a Noetherian poset. Okay. And so now the question is like, what is the algebraic manifestation of this? And there's a result of Cohen going back to the 60s, which essentially the Noetherianity of n star implies that the infinite variable polynomial ring is S infinity Noetherian. So I'll state what the result is. So let I be any ideal in the infinite variable polynomial ring stable under the action of the infinite symmetric group, where the infinite symmetric group acts on x by sending x sub I to x sigma of I and extending it linearly and making the ring homomorphism. Then the theorem is that the ideal I is generated by finitely many polynomials in I and their infinite symmetric group orbit. Okay, so and that's what I mean by when I say the infinite variable polynomial ring is S infinity Noetherian. So hopefully the statement is clear. So for example, if you take the maximal ideal, x1, x2, x3, and so on, it's generated by x1 and its orbit under the symmetric group. So this is a fairly important result and rediscovered a few times as well. And so what Cohen uses was to, given a group, you can look at the set of all polynomial identities on that group. So all kind of identities that all group elements behave. So for example, if you look at an abelian group, then one polynomial identity is that AB equals BA. And this is not only for generators, but all elements satisfies the relation. And he essentially proved that for a big class of groups, there are finitely many polynomial identities such that every other polynomial identities on these groups can be kind of deduced from the finite ones. And this was the key kind of technical result that he needed to prove it. And then Aschenbrenner, Hiller, and Sullivan needed to prove some certain ideals coming from like algebraic statistics had sort of this finite basis property. And let me just again sketch how you prove these results. So first you can, instead of working with the infinite symmetric group, you work with the increasing monoid, which are the set of functions from n, the natural numbers to itself, where sigma of I is less than sigma of I plus 1. So it's a set of strictly increasing functions. So this increasing monoid also acts on the n variable on the infinite variable polynomial ring, where if you give me a function f from n to n, it sends xi to xf of I. So the only difference here is that, for example, the ideal generated by x2, x3, x4, and so on, though that will be stable under the action of the increasing monoid, but it is not stable under the action of the infinite symmetric group. So the set of ideals which are stable under the action of this inc is there are more of them. And so it suffices to prove the statement of the theorem with S infinity replaced by the increasing monoid. And the key observation is that if you give me two monomials with exponent vectors I1 through In and J1 through, maybe I should have said Jm here. So this n should be m. The monomial m prime lies in the inc orbit of the monomial m, if and only if I1 through In is less than J1 through Jm as words in n star. Okay, and so therefore, now Higman's lemma will, from the previous slide, will give you Noetherianity for of this infinite variable polynomial ring with the S infinity action, and in fact the inc action, similar to how we got Hilbert's basis theorem from Dixon's lemma. Right. So now I want to give a non-example of a poset which is not Noetherian. So if you take the set of finite graphs with the subgraph ordering, so we say two graphs G1 and G2 with and G1 is less than G2 if G1 is a subgraph of G2. So the set of all finite graphs with this ordering is not Noetherian. And the kind of the key example to keep in mind is you have an infinite sequence which is 2 cycle, 3 cycle, 4 cycle, 5 cycle, by n cycle I mean you have like n vertices, 1, 2, 3 till n, and you connect I and I plus 1 and go on till you connect n and 1. So distinct cycles are not subgraphs of each other. So these are pairwise incomparable. So this gives you so the ideal generated by these distinct cycles are all will be infinitely generated in this poset. But there is a celebrated result from combinatorics, which is the Robertson-Seymour theorem. It's also called Wagner's conjecture, which is that the set of finite graphs under the minor relationship is Noetherian. Where one graph is a minor of another if the allowable thing is not just taking subgraphs, but if you have two vertices which are connected by an edge, you can kind of identify them. Okay, so there are more operations, which means the the minor relationship it makes the subgraph order. It's a refinement of the subgraph ordering. And if you look at this previous infinite sequence that I had given, you can obtain the n cycle from the n+1 cycle by just contracting the edge, say, n+1, for example. And so this would still remain, this would not give a counterexample in that case. But it's a very hard theorem. And let me just say that the algebraic manifestation of the Robertson-Seymour theorem is still not known. There is a specific conjecture about a specific representation category which we would expect to be Noetherian, and if that was true, it would imply certain uniformity results for homology of graphs and so on. But I instead want to now focus on the non-Noetherian example, the subgraph example that I talked about. So this actually gives a folklore counterexample, which I will now explain. So if you consider the polynomial ring R equals K adjoint Xij with I less than J, and Ij allowed to be in N. So this is again an infinite variable polynomial ring, but the action of S infinity is different. Now S infinity acts on Xij by sending it to X, so sigma acts on Xij by sending it to X sigma of I, sigma of J. Okay, so if you look at, this, it has essentially two orbits. When X, it still acts transitively on the set of permutations, set of variables. But now the key observation here is that monomials here correspond to graphs, where Xij, the variable, just means that we have an edge between I and J. Okay, that's kind of how I'm thinking about. So I'm thinking about if you give me a monomial, I'm going to build a graph out of it, where every time Xij occurs in the monomial, I will connect the vertex I and J. Let me just take a. And the graph is on the set of natural numbers. So division of monomials here correspond to the subgraph relation. And S infinity action just means that you can forget the labeling of vertices. Then if you look at the ideal generated by the monomials, which correspond to all cycles. So if you look at Fij equals Xij square, Fijk equals Xij, Xjk, Xik. So, I'm thinking of this as a cycle because, Xij, Xjk, Xik will correspond to an edge between I and J, J and K, and I and K. So that forms a cycle. And this is not generated by the S infinity orbit of finitely many elements. So because of what I essentially said in the previous slide. And what that says is that this question of, if you give me an infinite variable polynomial ring with some action of a group, is it Noetherian or not with respect to that action of the group is not like always true. It's a subtle question. And the previous counter example suggests that S infinity is too small. And Snowden, I think, was the first to recognize that the correct group to consider, and even for the sake of most applications, is this infinite general linear group, where I just take the co-limit of all GL and K with one n by n invertible matrix sitting inside an n+1 by n+1 matrix with a 1 on the bottom right entry. And morally what's happening is that unipotent elements in GL permit us to break cycles. So for example, if you take the Lie algebra element E13, you can write x12 square as, so E13 will act, it's a derivation. So E13 of x12 square will be 2 times x12 times E13 acting on x12, which is just 2 times x12 times x23. Okay, and so you've taken a 2 cycle that looks like this, and you've made it into like 2 edges connected at like one vertex, which means that at least if characteristic of K is not equal to 2, you can get all other cycles by just now adding, if you multiply this with x13, you'll get another, you'll get a 3 cycle and so on. So we've essentially shown that if you consider the GL stable ideal generated by x12 square that will contain all higher cycles, at least in characteristic not equal to 2. Okay, so I'm now going to like introduce what GL algebras are and so on. But so just to reframe, just with some combinatorics, we have shown that finitely generated commutative algebras in the category of nice enough representations of the infinite symmetric group are not Noetherian in general. And our question is whether finitely generated commutative algebras in the polynomial representations of the infinite general linear group are Noetherian or not. Okay. Any questions? Okay, I'm gonna move on. So now I'll introduce what GL algebras are. So a GL algebra A is a K algebra A with an action of the infinite general linear group such that A forms a polynomial representation of GL. And by a polynomial representation of GL, I just mean in characteristic 0, I mean applying a Schur functor on the standard representation of GL, which is just K infinity, which I identify with K E1, with basis an infinite dimensional vector space with bases E1, E2, E3, and so on. And in characteristic P, there can be more polynomial representations because the Schur functors are not irreducible. But we don't have to get into like the full details of it. So main examples to keep in mind are sim W, where W is a polynomial representation of GL. So for example, you can take, so V here is a standard representation, and you can take the symmetric algebra of V direct sum V, which I identify with K adjoin with x1, x2, xn, and y1, y2, yn, and so on. And GL acts on the set xi on its own, and it also acts on yi on its own. Okay, so there are interesting there are interesting ideals like the ideal of minus x1, y2 minus x2, y1, which are stable under the action of the infinite general linear group. Then you have the symmetric algebra of wedge 2 of V, which is the example that we were talking about before, a K adjoin Xij with I less than J. And the infinite general linear group acts on it in an appropriate fashion. And then you can have other infinite polynomial rings with with sort of 3 indices, and the infinite general linear group will act on, depending on how it acts on V tensor 3 essentially. So let me give a brief sort of history on like how, at least in characteristic 0, these were studied sort of in a systematic fashion. So let me just say in the 80s, many people were interested in ideals in GL algebras in characteristic 0. And primarily because because they wanted to study ideals of minors. I mean, that's really the reason. And in these 3 cases, at least, Abiasis Delfra, and De Concini, Eisenberg, Procesi, they had looked at the GL, they had looked at the lattice of GL stable ideals, and they had proved that the ascending chain condition holds for the lattice of GL stable ideals. And let me just say that, okay, before I move on, let me just say that if you want to essentially understand ideals in these rings, especially in, let's say you're in characteristic 0, you kind of have to know how plethisms work in characteristic 0. So for example, if you're looking at the symmetric algebra of wedge 2 of V, you first have to know how to decompose sim wedge 2 into irreducibles, sort of morally. And that itself is a very hard problem, which is why this problem is fairly difficult to kind of understand whether or not the Noetherian result holds. In these 2 cases of sim2 and sim wedge 2, these plethisms are known actually. These are one of the few cases when we can explain, we can say what the plethisms are. And that was used by Abiasis and Abiasis Delfra to study this reasonably well. Whereas De Concini, Eisenberg, Procesi, they don't classify all ideals. They just are able to look at sort of GL cross GL ideals in it, but whatever. And then Sam Snowden and Nagpal Sam Snowden, they studied these rings as well as certain classes of modules over these rings in a fairly systematic fashion. And that's because, at least in characteristic 0, they are closely related to at least what are called twisted commutative algebras, or sort of combinatorial categories via Schur-Weil duality. And I don't want to get into the full details of that. I'll skip what I wanted to say there. But let me just explain how combinatorial representation theory makes the Noetherian problem fairly easy. So I will show that sim v direct sum v is GL-noetherian in characteristic 0. So the first observation is that by Peary's rule, all irreducibles S lambda occurring in sim v tensor v satisfy the condition that they have at most 2 rows, because sim of v direct sum v is the same as sim v tensor sim v. So you're essentially just taking tensor products of symmetric powers, 2 symmetric powers, and then you can just use Peary's rule to see that they can have at most 2 rows. So that essentially means that we get an order preserving bijection between GL stable ideals of sim v direct sum v and GL2 stable ideals after just restricting it to K2. And that's because if you have a 2-row Schur-functor, you kind of essentially see all of it by just restricting it to K to the 2. But now the right-hand side is Noetherian just by Hilbert's basis theorem. So the left-hand side is also Noetherian. And using Littlewood-Richardson rule, you can prove Noetherianity for certain classes of modules over not just sim v direct sum v, but if you take an R-fold direct sum of v, because the length of that will be bounded above by R, or if or the length of any Schur-functor occurring in this, or any bounded GL algebra, which are just any GL algebra where you can bound the uniformly bound the number of rows occurring of Schur-functors occurring in them. And let me just say that the outlined approach in the previous slide fails in characteristic P, but it is not too difficult to prove GL-noetherianity or even S-infinity noetherianity for these simple GL algebras using the poset noetherianity of like the words in n to the r via Grosvenor theory. The real difference between S-infinity and GL comes when you move to degree 2 GL algebras. So these are where you have the symmetric algebra of wedge 2 or symmetric algebra sim 2 or higher degree ones. Now, I want to say, so Snowden asked this question about Noetherianity of GL algebras. And even though we don't know the answer in general, Draisma proved a very important result, which is the following. So if you fix an infinite field K and assume you have a finitely generated GL algebra, he showed that the topological space spec A is GL-noetherian. By that, if A has an action of the infinite general linear group, so does spec A. And he showed that every descending chain X1 of GL stable closed subsets eventually stabilize. So ring theoretically, what this means is that if you have a sequence of GL stable radical ideals, they stabilize, or equivalently, every GL stable radical ideal of A is a radical ideal of a finitely generated GL stable ideal. Okay, so this is a topological version. It's like the difference between saying that a ring is Noetherian and the spectrum is Noetherian. And so he was able to prove it topologically. Let me just give an example. So if you look at sim2 of V, so I should have it in the spec. The spec of sim2 of V can be identified with the space of infinite by infinite symmetric matrices with a GL action given by G acting on a symmetric matrix by GA G transpose. By classical linear algebra, its orbit is just classified by the rank of that symmetric matrix. The rank of a symmetric matrix is a symmetric bilinear form. But note that the rank can be infinite here, but those infinite rank ones can have a dense orbit in the spectrum. So the GL stable closed subsets of spec sim2 of V are just given by matrices of rank less symmetric matrices of rank less than equal to R. And you can clearly see that this satisfies the descending chain condition. But the topological GL-noetherianity for sim3 of V, the spectrum of it, was only established in 2017 by Dirksen, Egermont, and Snowden. And it's a very subtle argument. And shortly thereafter, Draisma proved it for all finitely generated GL algebras. So Draisma really proved a very powerful result, and because there are many, many applications of this. So let me give a few of those. So fix D and let Xn be the default tensor product of K to the n. Tn. So, and you let Xn be a nice family of GLN stable closed subsets as n varies. Okay, so the kind of nice family that I'm thinking about are things like set of border rank less than equal to R or slice rank less than equal to R tensors. These are fairly important, both from like a compute, like an application perspective, but these are very interesting closed subsets in the variety of like default tensors. Draisma's theorem implies that there exists an N0 and finitely many polynomials F1 through Fr in the coordinate ring of just T N0. So when you fix N0, such that every larger closed subset is set-theoretically defined by pullbacks of just these finitely many polynomials along linear maps from K to the N to K to the N0. So it's essentially saying that there are finitely many polynomials such that the border rank less than equal to 5 tensors in any default tensor product. So in the default tensor product of any large dimensional vector space is defined by them. But this is only a set theoretic statement, not an ideal theoretic statement. We don't know the corresponding statement for the vanishing ideal. We only know this as a statement of varieties. Then a second result that we can get from Draisma's theorem is that if you fix R and D and look at an ideal generated by less than equal to R polynomials of degree less than equal to D in an n variable polynomial ring, then then its projective dimension has a upper bound capital N, which only depends on R and D and not on the number of variables that you're working with. Okay, so if you take 5 cubics in 1,000 variables or 1 billion variables, there is some bound on the projective dimension that is not dependent on the number of variables that you use for the 5 cubics. This is not at all obvious, and this was only proved quite recently. And this essentially, and there is a generalization to essentially an abstract ideal invariant. So there's nothing special about projective dimension. If you just give me any way of assigning an invariant for an ideal that satisfies certain properties, and the most subtle one is that it has to be semi-continuous along upper semi-continuous along certain flat families. But if you have such an ideal invariant, then this also satisfies the similar properties where you can bound it merely in terms of the number of variables, the number of polynomials that generate the ideal and the degree that they are defined in. And the key input is the topological GL-noetherianity of these spaces, which essentially parameterize ideas generated by a polynomial of degree D1, D2 till DR. And so the Draisma's theorem has been used to prove certain uniformity results like this. Okay, so now so let me just say that Draisma's theorem is not just about one specific class. I mean, it kind of answers Snowden's question in the sense that he was able to show that finitely generated algebras in rep-pol GL are topologically Noetherian. The scheme-theoretic variant is still open. And what I recently showed was that the scheme-theoretic variant of Draisma's theorem fails in characteristic 2. And I expect this to also fail in other positive characteristics, but have not been able to prove it. I don't know what to expect in characteristic 0. So more precisely, assuming the characteristic of the field is 2, I construct a strictly ascending chain of GL stable ideals in the symmetric algebra of wedge 2e, which is the ideal which is the ring that we were working with before. And now I will get to how to construct this. But any questions? Okay, I'll move on then. Okay, so let's just revisit the previous example. So this is the example which we got from the graphs. So what I'm going to do is I'm going to define these S infinity stable ideals where J sub 2 is x12 square, but I don't mean just x12 square, but xij square. So I'm taking the S infinity orbit of x12 square. Then J3 is the S infinity orbit of x12, x23, x13, which corresponds to 3 cycles plus the 2 cycles. So J3 contains all monomials of less than equal to 3 cycles. And similarly, Jn contains all monomials corresponding to less than equal to n cycles. And I define similar things. Now, J2 is clearly stable, and in characteristic 2, J2 is clearly stable under the action of the infinite general linear group. And that's because it's a Frobenius power, the second Frobenius power. So if you take I mean, the key point is that a plus b square is a square plus b square in characteristic 2. So if I act on x1, 2, it becomes a sum of other variables and you square it. It just becomes a sum of squares. But when you look at J3, and can you see what's written on the top?
Yeah.
Okay, so wait, I can't see it, so I'm not able to. So yeah, okay, wait, I think I remember what was written there. So now when you take J3 and apply this Lie algebra element E14 and expand it out, what you get is, if you look at this three cycle and apply this Lie algebra element, you get another a binomial expression, which essentially graphically looks like this. So I started with 1, 2, 3, and it kind of like first breaks this edge and puts it along with 4, and it again breaks this edge 1, 2 and puts it along there. Okay, so we get that this kind of monomial, this binomial must also be in the GL stable ideal they generate. But this clearly is not contained in J3 or J2 because this doesn't have a subgraph that is a cycle. Now the key observation here is that, okay, if you forget this 2, 3 edge, which is common in both, you have this plus this. And okay, how do I motivate this? Well, let me just say what the answer is. So somehow if you now impose the Plucker relation, okay, what that means is this 2 binomial can be written as, so essentially what this means is that the x12, x34 plus x13, x24 can be rewritten as x14, x23, which is this plus this. Okay. Now there is a 2 cycle here, which means if I am able to impose if I impose the Plucker relation further, this problem element that we had will actually be in J3 because it contains a 2 cycle. Okay. And let me now rewrite this. So for first J1, I let it be the Plucker relation, but I also let it have xi j xkl plus xik xjl plus xil plus xjk. Then I now look at J2 with by adding the Plucker relation and continue as before. And the key two results are the ideas Jn are now become GL stable. And you also have to check that the ideals Jn are all distinct because now you have added the Plucker relation, which is in low degree, and somehow it could have collapsed all these Jns to J3 or J4, which does happen in other characteristics. So the key point is that in characteristic 2, by just imposing the Plucker relation, you get that the ideals Jn are GL stable and the ideals Jn are all distinct. And the idea is essentially what I just showed. It's a combinatorial argument. And let me just show a picture which might help. Let me just reshare what I'm. Wait, so so what essentially happens is that if you take a bigger cycle, and I start with this cycle 1, 2 till in, then and you can see the picture, right, that I'm showing.
Yeah. Yes.
Okay, yeah. So what happens is that you get 2 other n cycles, and then you get 2 other a binomial term which is does not contain a cycle, but you essentially apply the Plucker relation to these 2 edges to rewrite that as you kind of cross those 2 elements, and then that will contain an n-1 cycle, which is kind of similar to what happened in the 3 cycle case. And let me just get back to this. Sorry. Wait, I have to control it. Let me share this again. Okay, so these 2 results together imply the main theorem. And I want to explain, if you try to just generalize this as this, it won't generalize to other characteristics, but I'll explain how I expect this will generalize to other characteristics. So this example is actually coming from invariant theory. So if you look at the GL equivariant map from sim wedge 2 of V to sim V direct sum V, where Xij maps to the maps to xi yj minus xj yi. The image of this map is the SL2 invariant subring of S. And it is well known that the kernel of this map is generated by the Plucker relations in any characteristic. Essentially, this means that there's a nice, and this goes back to like classical invariant theory. Like everything that I'm saying here is like from at least the 1890s, but probably even before. This gives a nice graphical basis of the invariant subring of S, the SL2 invariant subring of S, given by essentially what are called non-crossing finite graphs with vertex set n. And I'll just say how you associate to this non-crossing finite graph. So if you give me this graph and the tree here is supposed to indicate that there are 3 edges between 1 and 2, you associate to that x1, y2 minus x2, y1 cube, and you have 3, 4, which you associate x3, y4 minus x4, y3 square, and so on. And non-crossing just means that you can't have, like, if you put it all in a line, you can't have any edges crossing. So you can't have the edges 1, 3, and 2, 4 in your graph, because that will make it cross. And it's the whole point is that the Plucker relations allow you to resolve crossings like this. Now, this is a well-known fact. So what I was looking at was that I was looking at the map from by composing this map phi with the map from S to its quotient, where you kill the pth power of the ideals. And the reason is that, okay, I was not actually looking at that. I was actually looking at the map from this to, in characteristic 2, the right-hand side of pi is the exterior algebra. So I was really looking at sort of exterior algebra invariance, which is so just to kind of connect back to what I initially said. And what I realized was, so it was sort of accidental that then I realized that the ideals Jn, where these ideals of cycles are all in the kernel of this, and they did not generate, they were, they formed a strictly ascending chain in characteristic 2. So that's kind of how I came up with this example. But and let me say that the ideal, the whole kernel is not this union of all the JNs. There are more things in the kernel. But in characteristic k greater than 2, if you look at pi circle phi, I suspect it is also not finitely generated, but the combinatorics just becomes like much, much more difficult. And I have not been able to like get a full handle on it. And I don't have a good, I don't have a good explanation. In the characteristic 2 case, I could say that you can just like kill all the cycles and look at all the cycles. But in characteristic even 3, I don't really know how to get at a good infinite chain of graphs which are all in the kernel and don't generate each other. But yeah, that's all I had to say today. So I'll maybe stop right now.
Any questions for the speaker? That's not the case. Let's thank him again.
So how does the Cherval duality sort of fit into this framework, generally speaking?
Yeah, so generally speaking, the way that it works is that if you give me a module over the infinite variable polynomial ring, let's say, you look at yeah, okay, here's what I should say. Let me just share the screen and maybe I can. I think this is, wait. Okay, this is where I was saying. Okay, so if you, but Cherval duality is a functor from the category of polynomial representations of GL, the infinite general linear group, to the category of sequences of, the representations of sequences of symmetric groups. Okay, so, and it's a symmetric monoidal functor in this with the on the left side it is given by tensoring representations of the general linear group, and on the right side is this induction product. So you can and these and on the right side, commutative algebras have been studied in various contexts. I think Joyal studied it as calling them species or something like that, I think. And most of them can be seen as can be seen as combinatorial categories. So for example, in the characteristic zero case, if you look at the symmetric algebra generated by the trivial representation in degree 1 as a representation of S1, that will be essentially functors from the category of Fi to K vector spaces, where Fi is the category of finite sets with injections. Okay. And this isomorphism, I mean, the way you should think about it is that multiplication by xn plus 1 is essentially giving you how the standard inclusion from n to n plus 1 acts in the combinatorial side. That's kind of how it more or less fits in characteristic zero. In characteristic P, you still have such functors, but it's not an equivalence anymore. And I kind of see the GL side as somehow certain nilpotent thickenings of the symmetric group side. I don't have a precise way of saying this, but these kind of Frobenius powers of the maximal ideal kind of give you nilpotent thickenings in some sense.
Yeah.
I don't know if that answers your question.
I understand. I mean, I've worked with the characteristic P side, so
Okay.
I understand that. Yeah, the difference. Great.
Other questions? If not, let's thank the speaker again.
All right. Was the recording done?